So what we are looking at is the user interface of TURBOdesign1, which is the 3D inverse design code, and we will use it to design the axial turbine nozzle. So following a top-down approach in the main tree, we start by filling in these specifications like the machine type, fluid properties, the inlet stagnation pressure, inlet velocity, and the blade number. And we can also see the meridional shape. Along with this 2D grid, which is automatically created and can be adjusted using these options here. And the solver is actually a 3D code, and even though we don't have a numerical grid in the tangential or the pitchwise direction, it solves the equations using discrete Fourier transforms, and that's why the code is very fast and numerically quite efficient. Now we support different types of blade thicknesses such as normal and tangential, and in terms of type we have the simple constant thickness as well as more complex distributions like NACA profile and flexible control points, which we are using in this case. And actually this possibility to specify thickness as part of the inverse design is very useful because it guarantees structural integrity, and if you have some existing thickness profile, then you can import that as well. And then we specify some fluid dynamic inputs, which is the blade loading, and this is the most important parameter for the inverse design method. And here we first specify the span-wise RVT star, which is the swirl distribution from hub to tip. So here 0 span-wise location is the hub and 1 is the tip, and we are imposing the span-wise swirl distribution at the leading edge and trailing edge of the blade row, and the distribution is free vortex, and so there is 0 swirl at the inlet, meaning a purely axial flow, and a constant value from hub to tip at the outlet. And if you recall the Euler turbomachinery equation, the difference in RVT star between the inlet and the exit gives you the specific work of the blade row. And this is important because it means that every design coming out of TD1 respects your required duty point. Now that the overall blade work is fixed, we need to specify how it varies from the leading edge to the trailing edge at the hub and shroud sections, and for this we have the stream-wise blade loading, which directly controls the blade surface pressure distribution, and this is basically the derivative of RVT star and directly relates to the pressure jump across the blade. And the loading at this point defines the incidence at the leading edge, and at the trailing edge the loading is always 0, which satisfies the kata condition. Now of course the present distribution is aft loaded, but you can easily make it fore loaded. And then the last important parameter is the stacking section. And so on one quasi-orthogonal at some stream-wise location, which is 0 for leading edge and 1 for trailing edge, you can actually specify the variation of wrap angle from hub to tip, and in that way you can lean the blade, and this will create a span-wise pressure force or gradient, and this is something that you can also use to additionally influence the 3D pressure field. So let's first start with 0 or radial stacking at 40% of the axial chord, which is close to its center of mass and helps to balance the centrifugal force. Now, even though the program is fully 3D, it runs very quickly within 5 seconds or so. and it gives you the blade geometry and also quite an accurate in-visit flow information. And this information is something that we can use to iterate on the design. So we can first take a look at the converged rotor geometry, nozzle geometry using this 3D plot here, and then we can create 2D plots of, let's say, surface pressure. At the hub, midspan and shroud, and then we can also relate the isentropic Mach numbers and isentropic velocities to some performance parameters which we can use to explore the design space. And you can see these performance parameters here in the project manager window. Such as indicators of diffusion and profile loss and end wall loss, and geometry parameters such as throat and lean angle. And then under this UDP section here, you can also use Python scripts to develop your own specific parameters. So if we now go back to the stacking section, we can now rearrange the control points to impose a compound stacking near the end walls like this. And still preserve the radial stacking at the midspan, as you can see here. And once we solve for the new design, we get our nozzle with controlled stacking, as you can see in this 3D plot. And if we now compare the static pressure plots with the radial stacking design, then clearly the controlled stacking has reduced the loading at the hub and shroud, while there is no change in loading at the midspan. And as a result, the performance parameters show that there is a major reduction in the end wall loss without much impact on the diffusion ratio and profile loss, which is exactly what we want. And then finally, the geometry can be directly exported from TURBOdesign1 to different format files that are needed for mesh generation, such as curve files for TurboGrid or step files for ANSYS Mechanical.